Okay, Unit 3, Assignment 3. Should have checked your answers. So here we got some graphs. Now the big thing I showed you guys in the lesson is that, I don't know, it's kind of hard to remember what exactly these look like, especially if it's been a while. So you kind of want to come up with a good strategy that'll work long term. So long term, what you should do is you think, oh, well, let me graph the inverse function, which would have the same base but be an exponential, which has a horizontal asymptote and goes through 0, 1. This is something you already got to remember anyways. It's something that you can probably remember easier. So then we're going to flip it across 1, 0, across y equals x. Anything that's y becomes x, anything that's x becomes y, so the horizontal asymptote becomes a vertical asymptote. And then it should look like it's a mirror image across this. So, that's the way I do it. Now you got to answer, is it increasing, decreasing? This is increasing. Is it concave up or concave down? It's concave down. What's its range? Negative infinity, positive infinity. Asymptote. Vertical asymptote. X equals 0. You need the x. So there you go. Now natural log is really just log base e of x. I'm going to use the same trick. I'm going to be like, all right, I'm going to graph e to the x. It's basic exponential growth equation. Goes through 0, 1. Has a horizontal asymptote y equals 0. So then we're going to flip it across y equals x. So 0, 1 becomes 1, 0. Horizontal asymptote becomes vertical asymptote. Y equals 0 becomes x equals 0. And this is your final graph. It is increasing, concave down, range is negative infinity, positive infinity, and asymptote is x equals 0. All right. Next graph. Let's see. So log, this is log base 10, it's common log. So we're going to start with y equals 10 to the x, exponential. Horizontal asymptote, y equals 0, goes through 0, 1. Now we're going to flip it across y equals x. Get a vertical asymptote instead. So this is just log of x. Now the 2 multiplies all the y values by 2, which just really makes it look steeper. Now it should still go through this, but it's gonna look steeper. And the minus 3 brings everything down 3. So we're gonna keep track of that x-intercept, and yeah, kind of looks like this, I guess, something like that. Doesn't need to be perfect. Definitely, still has a vertical asymptote at x equals 0. So this one is increasing, concave down, range, negative infinity, positive infinity, and asymptote is x equals 0. All right, good. Try the next one. Now, the inverse graph would be 1/3 to the x, which is the same as 3 to the negative x. So I'm going to use a bunch of tricks on this one. All right, so that's going to be 3 to the x, goes to 0, 1, horizontal asymptote y equals 0, and negative flips it. That's where the 1/3 is, actually decay function. Then we're going to flip that graph plus y equals x. So 0, 1 becomes 1, 0. Horizontal asymptote becomes a vertical asymptote. It's this decay graph, so it looks like that. And then the negative flips that graph upside down. So this is your final answer. And so it is increasing, concave down, range, negative infinity, positive infinity, asymptote is x equals 0. There you go. So I don't know, I'm just very systematic about this. By the way, if you become better and better at this, it's going to help you on the rest of this chapter as we explore other shapes. So this is log base e, so I'm going to go with y equals e the x first. So 0, 1, horizontal asymptote, y equals 0. These are things I need labeled and drawn on your picture. Then you flip it, you get 1, 0. Vertical asymptote, x equals 0. Gets reflected across y equals x. Looks like that. The -2 moves everything to the right 2 units. So now we're at 3, 0. Vertical asymptote at x equals 2. And the graph looks like that. Then the negative on the outside flips it upside down. And then the +3 moves everything up 3. So our point that we're keeping track of is at 3, 3. So something like that. So it is decreasing, concave up, range is negative infinity to positive infinity, asymptote is x equals 2. So there you go, graphs. We got to do domain. We talked about this. Inside has to be positive. So that's it, but I want it in interval notation. Okay. This one, x minus 3 has to be greater than 0. Inside has to be positive, so solve for it. But the answer I'd prefer is 3 to positive infinity. Inside has to be greater than 0. The -3 is not inside, so the -3 actually doesn't matter. So those are all pretty quick. This one, inside, has to be greater than 0. So x equals 3, x equals 0. This is a rational inequality. So we're going to solve these like we did back in chapter 1. Line check, test the value. I like to test far right for positive, positive is true, false, true. So the answer is negative infinity 0, union 3 to positive infinity. Here we go. So we're doing work inside x squared minus 4x needs to be greater than 0. So this is polynomial inequality from unit 1. So we're going to do line check, find the roots, open dots, test the value, x equals 5, true, false, true. So negative infinity is 0, and 4 to infinity. Here we go. Hey, why don't we throw some trig in there? Inside has to be greater than 0. So when sine equals 0, 0 plus 180k. We want all the values from 0 to 360. 0, 180, 360. We can do line check. These are open dots. And we're only interested in 0 to 360. So I put these little brackets here because there are more dots. Keep going. I like test 0, but I can't. So how about 90? 90 seems good. Sine 90 is 1, which is greater than 0 is true, true, false, false, true. So the answer is 0 to 180 degrees, parentheses. There you go. There's the work. So that work from Unit 1's coming back. We got solving some log equations. So there's two scenarios we're looking for here. We either want to try to get log equal log, single log, set their insides equal, or log equal number, change it to exponential form. So it's really up to what we have here, but we got to combine these logs first, and then we can set their insides equal to each other. So that's the easy one, right? This one, natural log, divide, because it's subtraction. So you get 1/2 equals 3x, x equals 1/6. Now this one, we can't make a log equal log, so we're going to change it to exponential form. 6 to the x equals 216. So this problem becomes like the one from a couple of nights ago, where can you make the bases the same? See, I think this is 6 to the x, I think this is 6 to the third, right? 6 times 36, double check it, 6 36, carry 3 to 18 is 21, yep. Set the exponent equal to each other, x equals 3. So we're using some strategies also, potentially from previous assignments. So this one right here, we're going to set equal to that. Now to get the x by itself, raise both sides to the reciprocal power, because then that they multiply and get x to the first. Now you want to do the cube root, the 1/3 power first, and then the square. So you always want to do the denominator first. It just makes the number smaller. So this is cube root of 8, which is 2 squared, which is 4. Okay, this one we're going to change to exponential form, and it's pretty much solved. We just got to simplify it. So I'm going to do 27 to the 1/3 first, and then -2 afterwards. So that's the cube root 27, which is 3. So x equals 1/9. This one, now this one's a little different. You can do it a couple different ways, but the base is e. So it is asking, what do you raise e to get e to the 1/2? Well, 1/2, right? Or natural log of e, they cancel each other out, 1/2. You could do e to the x equals e to the 1/2, and then set the exponents equal each other, 1/2. Same thing. So a bunch of different ways. Okay. Change to exponential. So that's going to be x, 3 squared is 9, third is 27, 81, 1 over 81. Done. Now this one, we want to make it a log equal log, because all the terms have logs. So we got to bring that in first. So that's going to be log 2 to the 4th. That's a power rule for logs. Then we could combine these, because minus 2 to the 4th is 16 over 3. And then set the insides equal to each other. Okay. 20, we want to make that log equal to a number, because we have this number right here, right? No, it's got to be single log, so we got to combine these logs first by multiplying their insides. Then we could do, well, is log base 10. So 10 to the 30th equals x to the 5th. Now you might be like, oh my gosh, it's a big number. I'm going to take the 5th root. Why don't we just take the 5th root right now? There's a 1/5 power. Rules of exponents say you multiply those, and this is just x, 1 with 6 zeros, 1, 2, 3, 4, 5, 6. It's a million. All right, let's see this one. We're going to make a log equal log, but you got to bring this in first. And then we're going to combine these together by dividing. This is going to be x to the sixth. So we can set the insides equal to each other. So it's going to be 4 over x to the fifth equals 2. Now, I think you got to watch out. I did simplify this. We'll see if that works. Okay, so I don't think x can be 0. Be careful because it gives division by 0, but 2x to the fifth equals 4, cross multiply. Fifth root of 2, or 2 to the 1/5. Okay, this one, we got a bunch of logs. We got to bring the 2's in. And we could just start, those are going to multiply each other. It's x to the sixth times 3x, all divided by x to the fourth. We could just do this, combine all three of those at the same time. So it's going to be 3x cubed equals 10. X cubed equals 10 thirds. Cube root of both sides. X equals the cube root of 10 thirds. Now we could break that up into the cube root of 10, cube root of 3. And to get rid of the cube root, you don't multiply by the same cube root. You got to get a perfect cube. So it's going to be a cube root of 9. So you get a cube root of 27 on the bottom. So it's going to be a cube root of 90 over 3. Now this is fine. This is also fine. All right. And got a couple problems. Use your graphic calculator on. So we can't make these bases the same. So we take the log of both sides. Now, log base 10, the common log works really nice because we actually probably do this without a calculator, get at least an answer. This cancel and get x equals log of 2. Now, on your calculator, it's going to be 0.301. But, yeah, so that's one way of doing it. Okay, this one right here, take log. Now, the reason this works is you can move it out in front as an exponent because of the power rule. You got to put it in parentheses. So now if you want to solve, you need to distribute this. So you got 3x log of 5 minus 2 log of 5 equals log of 3. And then you need to solve by doing reverse order of operations. So x equals log of 3 plus 2 log 5, which you could combine if you wanted to, divided by 3 log 5. So that's the answer. On your calculator, it's 0.894. Okay. Now, if it has a base 10, common log makes sense. If it has base e, I would do natural log because it just cleans up nicer. Those cancel each other out. 4x minus 1 equals natural log of 100. Add 1. Add 1. Divide by 4. So there's your answer. Perfect. Exact. On your calculator, it's 1.401. 3 decimal actually. So that's solving exponentials where you can't make the bases the same. Use logs, use your calculator. Right, U.S. national debt is where X is the number of years since 1900. When will the debt first reach 1 trillion? Pretty sure it's past that, but whatever. Let's just play along. 1 trillion well, that's a million, that's a billion, that's a trillion. So we're using this model, and we're setting equal to the desired outcome that we're looking for, and then we can solve for x. So we're going to divide by 0.0515. Then we take like log or natural log or whatever. I would just do log of both sides. And so we can move the x in front and divide both sides by that. So x equals log of 1 trillion divided by 0.0515, all divided by log of 1.131. Now you can't combine these logs. Well, yeah, you can't just easily combine them, but on your calculator, this is 248.551, which isn't quite the answer because it says what year, when. Well, this is years since 1900. Or you could add 1900 and say in 2148.551, 3 decimal accuracy. There you go. So that's the homework. Hopefully you're getting good at your logs again. Definitely a common function that we're going to see a lot this year.